like it. Cool. The initial plan on this was to go through the index laws, but I made all of these curriculums well and truly ahead of time, and it seems a little inappropriate to be doing stuff like this, and we've been doing exam revision, especially because we don't necessarily have all that many Unit 1 and 2, or people doing Unit 1 and 2 that would need it right now. And so I guess unless you're specifically looking to revise some of the index law stuff, would you mind just going through the rest of, well, as far as we can, the exam that we've been doing?
Yeah, I'm fine with that.
Sounds fair to me. Cool. So for that, once again, I shall drop in the exam as well as the solutions if you want to take a peek at that for any reason. Starting with question 3. We'd finished, yeah, I think we did all of question 2 last time. So that's good. Let's just continue on with 3 then. So if you want to grab a copy of the PDF to zoom in at your own leisure, you've got that. Otherwise, starting with question 3a, we've got some sort of exponential. State the value of the limit as x approaches negative infinity.
Is the limit 5?
Is the limit 5? Yes, it is. Yeah. 2 to the power of negative infinity. You're essentially putting that as like a 1 over a massive denominator, and so the term disappears, leaving you with just 5. Yeah. Technically speaking, you can cas that out if you like. There's no real reason to, though, of course, if you can spot why it is what it is. Easy. Moving on. Derivative can be written like that. What must k therefore be?
I'm not really sure how to do this because
Mhm.
wouldn't the exponent be x minus k then as well?
Wouldn't the exponent be x minus k? Um, oh, no, okay. So you're thinking of another type of derivative. You're thinking about the power function derivative, x to the power of something. This is 2 to the power of x. Different rule. This is the exponential derivative, not the power function derivative. If you've got a copy of the, well, this actually won't show up on your formula sheet because formula sheet only shows you how to do like the e exponential derivative.
Yeah.
This is something where you'd want to just cas out the derivative and then compare what they've got written here to what you've got in your cas, and then you can just sort of see what k is going to be.
Oh, this is on Tech Avo, hey.
Yeah, tech active. Yeah. So I should have specified that last time. I was yeah. These are
Okay.
tech active.
Yeah, let me just quickly grab my CAS.
Yeah. Yeah. No worries. Hey, Pia, just to catch you up, the agenda was to do index laws, but it seems like there's no real point to do that at this stage, and so we're just kind of moving on with the past exam that we were doing last time. I'll drop both the solution and the exam document again if you don't have a copy from it from last time. And yeah, we're moving on to catch yourself up with question 3. We're on B right now.
Okay, so my CAS says that k should be natural log of 2.
Yep, and you'd be correct. Yeah, natural log of 2. So just straight up defining g of x into the cas and then doing derivative via cas, you'll have natural log 2. In fact, I can just sort of show it. You'll have natural log 2 times 2 to the power of x, and so obviously k must therefore be natural log of 2. Yeah, so exponential has a bit of a weird derivative sort of thing going on with it, where only the base of e is a clean derivative. Anytime you have a different base, you end up with what is, in most cases, just a natural log of the base that you achieve. Now, obviously, there's going to be some caveats around that. But yeah, just a bit of a weird little thing that's going on there. But okay, that's that. Part B, 1 marker, nothing really to give there. In fact, a fair few of these have been more markers. Part CI. A is a real number. Find, in terms of A, the equation to the tangent to G at that point A. So reminder, G is this function up the top, G of x. We're trying to take a tangent at some point A. We want to figure out the equation of that tangent. There's an easy way and a hard way for it. Remember, it's 1 mark, so if you can just get the answer, it'd be advisable to do so.
Is it 2 to the power of a natural log 2?
2 to the power of a natural log 2 seems short for a full answer. 2 to the power of a natural log 2. Oh, you're just finding the y value. No, what have
Yeah.
you found? Because there's no, like, we want the full tangent line equation, the y equals mx plus c.
Oh,
So,
okay, okay.
yeah.
Oh, okay, yeah. I'll just like put a into the derivative. Yeah,
Yeah,
no.
okay. Yeah, you did get the gradient. That was part of it, definitely. Yeah. I take it by the silence that people are doing it the long way. That or are stuck. One of the two.
Yeah, Chris, I'm a little bit stuck.
Yep. Okay, so easy thing off rip. Kaz has a tangent line function solver, and so all you have to do is define your function and force the Kaz to take the tangent line at whatever particular x coordinate that you desire. So in this case, the x coordinate was x equals a, and so I've just said x equals a. That's the intended solution of doing it. It's a 1 marker. They don't give you much lines of working out to try and do the full tangent line. If you were to try and do the full tangent line, you're going to have to do step 1, grab the derivative for gradient. So you've done that before. And then step 2, sub in the point to solve for y equals mx plus c. So, you're going to have to sub in x equals a into g of x to get the y value. Then you've got a comma 2 to the power of a plus 5. That's your y and your x. And subbing that into a tangent line function. Obviously, just by looking at this, pretty big. Trying to do that by hand, not particularly great. And so, yeah, the intended is just to do the tangent line function. This exists in the Casio as well. The order of these terms might be a bit different, but the point is you can still just do function, and then where am I taking the tangent line at. Anything to clarify further about that? If not, feel free to move on to part II, hence or otherwise. It's an important keyword. That'll also imply an easier way versus a harder way. The first hint I'll give is kind of a repeat, but that hence or otherwise is implying that the previous answer, so this equation for the tangent line that we've just created, is going to be at least a lot easier of a way to solve this question. So to expound on that a little bit, think about what that function actually is. Like it's a tangent line of x equals a. What does that actually mean you've achieved if you're taking or finding the formula of a tangent line for some random x equals a? You can determine what that's actually achieved. You'll see how you can then use it in II. Another hint, what we've just created is a generic tangent line that is associated with the original function, such that any value of a that we plug into this will give us the tangent line at x equals that particular value. And what we want to have happen is, at the end of the day, this tangent line has to pass through the origin. It has to pass through 0, 0. That means you're forcing a particular point that it has to pass through.
Is do sub in zero?
Yes, that is correct. Yes, subbing in 0. How are we doing that?
So you've already defined the tangent as g of x, right?
Yep.
So then you can just do g of 0.
Yep, that's part of it.
Then after, do we put into like a solve
Yes, we do.
for
Yeah.
0 equal to this thing?
Yeah, correct. So you're
Then solve
subbing
for
in.
a.
Yes, that's it. So it's not just x equals 0, it's also y equals 0. So it's
Yeah.
solving g of 0 equals 0, and we're getting our a value. Now this is supposed to be to some number of decimal places, so I'm happy to control enter on that one. And now that we have a, that's not quite the answer though. We don't want to find a, even though that helps a lot. We want to find the equation of the tangent under these conditions. So now that we have A, what can we do with it? Remember, to get a tangent line, you need some sort of y equals mx plus c. You're allowed to have y, you're allowed to have x. You're not allowed to have any other letters in it if you want a fully solved tangent line. On my CAS, g of x is the tangent line. There's only one thing in that answer of g of x that's stopping me from just writing that as my final answer. I only have y and x in it. It's one final variable in here that we have to somehow get rid of, and that's the a. If we knew the value of the a in that, we would now have a fully solved tangent line. What's the final step? We've solved for a over here. We need to get rid of a up there.
Do we put A back into g of x?
There we go. Yeah. Fast way to do that, just set up a define and grab a copy of this, and then just reprint g of x. Now that's going to look a bit nasty, so we're just going to control enter on that. And then yeah, so just to sort of recap what was happening, we had this generic tangent line. The only reason we can't give that as our final answer is because it's not really a full tangent line equation, or not, at least not a solved tangent line equation. There's a's in it as well. And so we want to force it to go through the origin, which means we're able to now figure out what our a value has to be to force it to go through the origin. And then all we do is just sub that back in. And then when you do, you'll get your tangent line formula like this. Now, we want to round this to 3 decimal places. So this, the gradient can be rounded to 3 decimal places, nice and easy. This really, really small coefficient on the end just fully disappears. Like this is e minus 13. It's effectively a rounding error. And so when all is said and done, this thing is considered not to have any coefficient because we're rounding to 3 decimal places. So we just have a look at the PDF. You'll see what was going on there. This is us subbing in x equals 0, y equals 0, doing a CAS solve for that specific thing. That gets us our a value, and then, well, we have our a. So you plug everything in and round. Cool with that? It's a bit of a weird one. You don't usually have this like sort of rounding error like coefficient that you can get rid of entirely. But yeah, this one was a bit special, this exam. It felt a bit weird how they really did this sort of stuff a lot, whereas most exams typically don't sort of focus on this sort of thing. Like again, in part D, it's another type of exponential use with a base of 2 rather than a base of e. I like to have these 2 to the x sort of things going on, which is very atypical. But that was the focus of this one. Anyway, new function, h of x. Part D, find the coordinates of the point of inflection for h, corrected to decimal places. There's a couple of ways you can go about this. The fact that it's two decimal places means it opens up a little bit more as far as what techniques you could use via CAS.
It's just a question.
Hmm.
At a point of inflection, like to calculate it, do we do double derivative?
Yep, that's totally one way of doing it. Yeah, double derivative being zero. Now, technically speaking, double derivative being zero is only a strong indicator that you have an inflection point. In Spesh Math, they take it a step further. So when you're doing the tech active in methods, you probably want to double check that with the graph as well. But yeah, double derivative being zero will sort you out in the most cases. Yeah, that's it.
Um,
Yeah,
I got X is well, I still need to put X back into the thing,
yeah,
but
yeah.
okay, so is the coordinate 2.05, sorry, it's 2.06 and negative 0.07?
Um, Negative 0.07 is good. I've got 2.08 as my answer. Let me just double check that's the case and I didn't just typo it. Huh, I typoed it. Nice. Yay me. Yeah, you're right. 2.06. Cool. Let me fix my answers. I'll write a note for that. 2.06 for 3D. My apologies. You did fine. And so what I was doing on the CAS there was just a graphical way of doing it rather than double derivative being zero. And so at least on this CAS I'm familiar where you just go analyze graph, inflection, and then you find your inflection point. Notably, this is not a stationary point of inflection. Any point of inflection simply just means where you wobble from being concave down to concave up or concave up to concave down. And so that's why it can be a bit trickier to identify whether or not you have an inflection point via double derivative. But it still works, right? Like if you have a look at the screen share again for the PDF and ignore the 2.08 that I've written there, instead imagine it being 2.06. Yeah, you're still just doing double derivative being zero. Cool. If there's any questions, let me know. Otherwise, part E, the largest interval of x values for strictly decreasing.
Chris, is it 0.49 and 3.21?
Yes, yes, it is. Nice. There's a couple ways you could have gone about that. Um, when I was doing it myself at some point, I had tried doing derivative being less than equal to zero. Um, I guess that was just too complicated for the CAS, and it just didn't give me a solution. And so what I ended up doing was doing just plotting it and then just seeing where's derivative equal to zero, and then just looking for the boundary in between those. The other would have been that you would have just sort of looked at the turning points. If you were able to identify either via the graphing tool or otherwise to grab those turning points, you could just sort of observe based on the graph that it was decreasing or strictly decreasing for that interval. Yeah, those are the main ways. Did you have any other method?
I just did the turning point method as well, so
Yeah,
no.
easy. Cool. Part F, Newton's method. Yeah, here we go. Yeah, this is how Newton's method should be tested, because otherwise, if they just want the answer from Newton's method, then you can just CAS solve it, and there's no issue at all. Um, if they do it this way, they kind of force you to use Newton's method because you have to give each of the individual x1, x2, x3 values as you're going through it.
Chris, if it's not too complicated, could you just tell me like what Newton's method is?
Yeah, sure. So Newton's method, I mean, it's on the complicated side, but that's fine. We're here to learn. Can I override this? Maybe I can. I like to define Newton's method in three scenarios. Actually, sorry, let's just roll it back. Newton's method is the repeated taking of tangent lines at some initial guess until you get closer and closer to some x-intercept. So for instance, let's say we can't use algebra to solve where this x-intercept is, but we know it's roughly around here. What I can do is I can take a tangent line off of here and then look at where it reaches the x-intercept. And then I'll say, cool, okay, I'm getting a bit closer. And so what I do then is I look vertically down from that x-intercept and then take my tangent line off of that x value. All right, take a tangent line off of there. And suddenly we're intersecting way closer to the actual x-intercept. And so again, I look vertically down at that spot and then take a tangent line off of that. And you can see how rapidly we are very quickly getting closer and closer to that x-intercept. That's Newton's method. As for how you do it, there is actually, if we scroll down on the PDF all the way to the formula sheet, you'll see it defined down here. Xn plus 1, so the next x-intercept, is given by the current x-intercept minus the y value at the current spot and divided by the derivative at the current spot. So, to set that up, I define a of x as the function that I'm trying to take the tangent line of. So in this case, it's going to be, well, I'm pretty sure it was h of x. Let me double check. Newton's method for h. Yeah, cool. Then from there, I define b of x as simply the derivative of a. That's going to give us our denominator. So d dx of a of x. Then from there, c of x is going to be my actual Newton's method. So that means I'm doing x minus a, which is my original function, over b, the derivative, over b, the derivative of that function. That sets up Newton's method in the CAS. From there, we have to look at the question itself. It's telling us that our initial guess is x naught equals 0. So that's what we sub in. C of 0, that's going to give us a value. Then we feed that value into the function. And then again, until you basically fill out the table or answer whatever other question comes up. So this first value here, negative 1.44, is the first x-intercept, x1. So that's the first entry in the table. Second entry, down there. Third entry, down there. And then you're sorted. That's how that one works. Is that all fair enough?
Yeah.
Yeah, at least as far as filling out that table. Now, if you were to repeat this a whole bunch of times, so keep feeding it in, maybe I should do it this way instead. Yeah, keep feeding it in. You'll see very quickly these numbers stop changing. And that's because we have found the x-intercept to some number of decimal places. Like, look at that. As soon as we've stopped changing, like, that's pretty perfect. If I then go ahead and try to solve where is h of x equal to 0, it's going to spit out that same value, or at least one of them. There's obviously 3 x-intercepts for this one. Since this was closest to the x equals 0 spot, it found this one instead. If you wanted to find any of these, you would have to choose a guess that's closer to those. And that's why, if it just wants the answer, well, you can see how you would just do a CAS solve and get the exact same thing anyway. That's why they ask it this way. Yeah, and I've got that written in the prescribed answers as well. I've written them as F2 and F3. Yeah, it's just sort of whatever. Plug and play, sort of. So part G is going to require a bit deeper of an understanding as to what Newton's method is actually doing. That's kind of why I had a little bit of a preamble there to describe what is the algorithm actually trying to achieve. It's this repeated taking of tangent lines at the x-intercepts of those tangent lines. That understanding will help you answer G. That's a very, yeah, there's a lot of layers to G, but that's one of the things you have to consider for it. Depending on how, oh, no, I won't give that one. That's probably a bit too much of a hint. Maybe I'll just ask instead, does anyone actually recognize this equation from having done it in a previous question, like in this paper? Okay. Depending on how you solved for the turning points, you may or may not have seen this equation. This equation could have been related to finding the turning points of the of h. I think that's as far as I'll give a hint for where this would have come from. At least for now.
It's the derivative of h.
It is a derivative of h, correct, yeah. So now
And
this is actually, yeah, go ahead.
I guess if you equal it to 0, it's not really an estimate at that point because that's just like that's just gonna be turning point.
Yeah, yeah. So what is it specifically about choosing a turning point that's bad for Newton's method?
Um, is it because like your tangent is like gonna be a flat line?
Yes, that's exactly what it is. Because Newton's method requires you to use the x-intercept of a tangent line to create the next tangent line. So if you've got a perfectly horizontal one, because you're taking it at a turning point, yeah, you can't continue. It's what they refer to in the book as a terminating sequence. It does not continue anymore. And so yeah, that's really good. One marker. It's one of the what do you call it? Separator questions. This was about a 21% pass rate, and I imagine that a lot of people would have stumbled here just simply because they might have used like a graphing tool to find the turning points and just they see this equation like, what the hell, where did this come from? um, you might see the similarity between the 2x and the minus x squared, and just from having done the previous, like way previous in like part B or something, like having done this, you might remember that natural logs had something to do with derivative of 2 to the x. Yeah, those are things you might be able to spot, but tough if you didn't use a derivative approach for before. But anyway, if there's any questions about that, feel free to let me know. Otherwise, H, where they've gone even more generic again. Completely generic exponential, completely generic power function. I'll give a warning up front. When I did this last time, when I was making these solutions, relying entirely on the CAS actually failed, oddly enough. So if you're getting these, like, if you're having these good ideas as to how you'd go about it and the CAS just gives you nothing, just know that it also happened to me. And we had to do a bit of a workaround. I just looked at the marking scheme, 3% pass rate, full marks for this. Probably because of that issue, with the CAS being a bit of a pain. Anyone got any ideas they'd like to share about what would be appropriate? Or like what kinds of things have to be true to make this, what kinds of directions we could take it in?
Chris, because it has like the same like sort of form to the to h of x, could we like sort of compare and maybe find an idea from there?
Yeah, yeah, certainly. It has identical form basically. You're just choosing n to be something other than, what was it, 2? Yeah.
And is it also like I think h of x also has like a local minimum, right?
Yeah. Yeah, because it's a cubic kind of like shape. It's got a local minimum that's sort of dipping below around, oh, what was it again? We had the value. It was x equals 3.21-ish. We're told there is some positive n that would force that local min to now be on the x-axis.
So it needs to like strictly decrease until the
Mm,
x-axis, basically.
yeah, basically. There's a couple of things that tells us, forcing a turning point to be on the x-axis. In terms of equations, what could we start creating?
Derivative.
Yeah, derivative is, well, that was at least my first guess. Well, my first approach at it. Derivative being 0, it's a turning point. Makes sense, right? Um, Unfortunately, if you just do that, it kind of doesn't like it. So if I show you what I was sort of going about, grab derivative, chuck it in a solve. Seems like I should be able to rearrange for x. I guess it just doesn't. I'm pretty sure it's spinning wheels, so the Kaz just thinks really hard and then gives up. So I'd rather not break the Kaz to show you, but feel free to have a look and see what happens after this. So just doing derivative equals 0, not super helpful, at least in this case. Alternatively, forcing it to be on the x-axis tells us a little bit about the function at that spot. If we know it has to be on the x-axis, what's another thing equation-wise we can guarantee? How do we know that something's touched the x-axis? Just any function. If I create just some basic linear, and I tell you to find the x-intercept of it, y equals x plus 3. How do you get the x-intercept?
We just make y 0 and solve
Yeah,
for x.
that's it. Y is 0, solve for x. Cool. So if we know this is going to be on the x-axis, then we know that y is 0 at that spot. So going through there, you can try to get the Kaz to solve that, and still ended up being a bit of a pain, oddly enough. If you try to solve a function equals 0, it's just not going to let you do it. And so basically you just sort of have to do it by hand. All right, so if you have a look again at the PDF for the answers, you can sort of just do it by observation. If you have n of x to n to the power of x minus x power of n, and you just sort of flip the terms, you can see there's an easy solution there, which is that if n is x, then this is a solved equation. And so that gives you a way to essentially remove one of those variables. And it turns out that was enough to now make the Kaz start playing nice. So you just sort of, I don't know why I felt compelled to, oh, maybe this is still broken actually. Yeah, why did I keep going here? You say f dash of n equals 0. Let's find out. That one I'm not too sure if that bricked or not. So this was, we need to redefine the function. New one, f of x is equal to n power of x, oh geez, n power of x minus x power of n. Just regular derivative of it. Derivative of f. We'll call that, I don't know, v. So when you do a Kaz solve, why does this break? So this would be v of n, because we're saying x is equal to n, equals 0, comma, n. Oh. Oh, right, because you don't want a decimal, you want e. Is it going to give me e? It's not going to give me e. Yeah, okay, so that's why I did it by hand. Because if you do try to solve for n that way, you might recognize this as e. You need to be very particular with knowing your values if you're going to do that. But yeah, since it didn't say to some number of decimal places, you'd either have to recognize that string of decimals as e, which maybe not that hard to do. If you know that e is roughly 2.7, that should probably spark something, given that you're working with natural logs. Or the alternative, of course, is just to do your algebra. So if we have a look at what that algebra would look like, let's see. So this is us subbing in x equals n, equating the derivative to 0. The next stage there was simplifying this index. So n times n to the power of n minus 1. That's just, cancelling down that negative 1 on the power. You've now got a common factor of n power of n. You can now take out the front. This is now... I just heard a noise there. Was that a question?
No.
Yeah. Okay. You now have a null factor law. So either n to the power of n is equal to 0, which, I mean, never, because you've got something power of something. Well, now I'm curious. 0 to the power of 0. I forget what's going on. Yeah, undefined. Cool. Which is just not going to really work out. And so the only other option is natural log minus 1 is equal to 0. And then that's not nearly as bad to solve. Natural log of n equals 1. Rearrange. N equals e. I don't know why the CAS had problems with this. This doesn't seem like it should be hard for it to do, but apparently it is. Yeah, I don't know. Just sort of failed a bit. It's another reason why this exam I felt was kind of trippy, because it was built in a way where the CAS just sort of didn't like doing any work. So these are the kinds of troubles you're going to have to troubleshoot in the real thing, and have these sort of different approaches. And that's why I've included them in the solutions. Like you can see, natural step, derivative equals 0. No, didn't do shit. All right, cool. How about function equals 0? No, still didn't do shit. All right, next thing up, just try to do some stuff by hand. And that, somehow ended up working out fine. So having to, at least for those more complicated questions, having to have something in the back pocket that you can try a different angle on becomes really effective for trying to solve those really tough questions. This is only going to matter, of course, if you're shooting for the highest possible mark. If you're just following the guides that we have here, like you'll crush 90%, we'll call it 70% of the exam, and then the rest is going to be how deep do you understand the questions, how many ways can you attack things. It's kind of why I like to show the other options. But cool, that does take us to the end of that question. We'll make a start in question 4. Probably won't get all that far with it. Got about 10 minutes left, but we'll see. Manufacturer, tennis balls. Diameter is normally distributed, mean of 6.7, standard deviation of 0.1. Find a probability d greater than 6.8. This should be nice and fresh for some of us. Yeah, there you go, Peter. Normal CDF. Correct. Yeah, so whenever you're trying to find a probability of something that is normal, it is always CDF, right? Find probability, you're using normal CDF. So, oh, of course it closes on me. I hate that the CAS does that. If you time it just right, you can input something as it's powering down. And then you see it do its input, and then it turns the screen off. Anyway, normal CDF, lower bound 6.8, because we're trying to do everything greater than 6.8. Just, of course, be keeping in mind that you have to do a bit of weirdness by using infinities when it comes to normal. Even though we can't have an infinitely long diameter for a tennis ball, we do have to put it in there for the model to be as accurate as possible. Technically speaking, if you do try to think about some realistic upper bound, you're not going to have any noticeable change in your decimal places, but why go through more effort trying to figure that out? Yeah, and we're going to get 15.86%. Corrected to 4 decimal places. If there's any questions about that, feel free to let me know. Otherwise, part B. In fact, one thing I will touch on that, mean of 6.7, standard deviation 0.1. 6.8 is one standard deviation removed from 6.7. So that 15.8, as a result, should really ring a bell there if you're used to doing your tech-free versions of doing this, where you do plus minus 1 standard deviation, splitting it, and then doing whatever's to the right of that normal distribution. That'll be a number that you see quite often in tech-free, normally 16%. Anyway, part B. This is the other typical normal question.
Is this going to have something to do with confidence intervals?
Not particularly, because confidence intervals are typically symmetrical either side of the mean, whereas this one is literally saying larger than entire, like 90% entirely. So basically, what this means is if I turn on my phone again so I can draw, um, a visual of what's going on here is that you have your normal distribution, and you want to find the value of A that's bigger than 90% of all the other possible values, which means left of here all the way to infinity accounts for 90%. And you want to find what this is. There's a very specific has function that does that. Whereas confidence intervals would be like having another boundary here, and they'll say 95, 68, or 99 for in between there. It doesn't shoot all the way out. Inverse normal is correct. Yeah, that's good. So whenever you're trying to solve a particular x-axis value, in this case it's d, the diameter of a tennis ball, the thing that's on your x-axis, that's always going to be an inverse normal. Now, for TI Inspire, you have to always point left, so this picture is perfect. You can just say 90% is your area, and then everything else you just plug in as per your normal statistics. So inverse normal on the CAS, number 3, 0.9, mean is 6.7, standard deviation is 0.1. That area is always pointing left. 6.8. For 2 decimal places, of course, you're going to round that now to 6.83. If, and just for the recording, those using Casio, let's see, does this pen actually tap things? Maybe. Yes, it does. Distribution, inverse normal. They call it the inverse normal CDF, and they have this option where you can choose whether it's pointing left or right. Center is also a cool one, but that's more so for the confidence interval stuff that you were talking about before. Probability is the equivalent area, right? So it's how much is left or right, and then obviously your standard deviation and mean. Right. That's about it for that one. If there's any questions, let me know. Otherwise, pay attention to part C, which may or may not change the probability. Reminder that anytime you have this indent, it's pretty likely they're changing something about it, such that it's no longer going to be just normal or just whatever the previous thing was. Now I say pretty likely. I don't necessarily guarantee it's going to change every time, but usually when they've got a new heading there, they've done something to try and change the scenario that might convert it to a different probability type. It will eventually be binomial, just not quite yet for C. Yeah, so we are putting them into these individual containers, which, yeah, very indicative of something like binomial or at least discrete, because now you've got these fixed sizes and number of balls. However, the question that's being asked here is any random ball fitting through the opening of the container. So we need to first find the probability that it can fit through a container, not just that some number of balls, like how it's phrased in D. Like if you're told, find the probability of 4 tennis balls trying to fit through the container, that's when it starts being binomial. When you're working on like an individual basis with no n value, you sort of just either defer to, yeah, I can't really give a general answer there. Typically, you're just deferring to whatever the previous probability was. So if I were to sort of work through what's the thought process there, tennis ball fit through the opening if it's smaller than 6.95 centimeters. What's the probability of it being smaller than 6.95 centimeters? Well, we can see that diameters are normally distributed. So if we're trying to figure out the probability of a diameter, we now know it's a normally distributed thing. It only becomes binomial once you start looking across more than one given scenario. So this one in particular, if I just pull up the answers because we're about to run out of time, that's just another CDF. Oh, sorry. It is still another CDF, just not that CDF. It's this one. So smaller than 6.95, upper bound 6.95, negative infinity for your lower, and then everything on from there. And then to cap it off, just because we're about to run out, this is where you're now doing the binomial CDF. So you're told your random selection is 4, so that's your n value. That's the n spot. At least 3 fitting through the top of the container means that you want to have a minimum of 3, an upper bound of 4. And then this thing I've done in here is just this, right? That's the probability of it fitting through the container. I don't like putting the rounded value in here because it can cause an issue. I don't really like doing or playing with fire as such to how many decimal places I'm going to put into this thing before I before I call it. So I typically just plug in the entire entry that you've put in the previous answer in that spot. And what that ends up looking like is, so if I just do, even if we just use this normal CDF, it doesn't really matter. I'll typically go binomial, put in my number of trials, put in some dummy whatever for probability of success, something I can recognize easily. Lower bound 3, upper bound 4. And then where that thing appears, just cut it out and then replace it with the... You can pick any of these. They're basically the same. This is slightly better to pick because I'm pretty sure that's rounded. But, you know, if you're going to have an error rounding to that many decimal places, then something's clearly off. Now, this is not going to be the right answer. I picked some random CDF that we did earlier. But that's basically how you create that without, you know, having a lot of trouble to achieve that. That's about it. We've hit time there. So if there's anything that we've covered today you'd like me to dive into a bit deeper, feel free to let me know. Otherwise, I'll let you enjoy the rest of your day. And I'm hoping this was a lot more productive than doing index law stuff.
Thanks, Chris.
No worries. Take care.